remember that last time when we were talking about trapped orbits, one of the things that was absolutely imperative is that there be a spiral pattern or some other perturbation, right? So in that, in that drawing that we had this spiral arm, and then we had co-rotation kind of going like this, and then we had our trapped orbit that was doing like this, right? And then when we were talking about the physics, that star is just gonna, oscillate forever and ever and ever and ever and ever. So for a long time, and I think I mentioned this, for a long time, people just assumed that it really wasn't that important because anything that started here was gonna end up here anyway. So it might be some region that was just gonna kind of get smoothed out as stars sort of moved around, but nobody expected it to be very big, meaning the region where stars were in these trapped orbits, and nobody expected it to have any long-term impact on the galaxy. Now, that becomes questionable when we realize that spiral arms themselves don't live forever. So now you've got a star that starts here, it's doing its thing, and the spiral disappears, and so it's permanently in a different place. Why do we care about that? Well, it can have a lot of impact on the evolution of the disk itself. So let's one transient spiral arm, but you have multiple generations of spiral arms where stars like hopping out like this. Then there's, as of now, there is no mechanism to make these spiral arms go away once they've formed. And I think and I've told you, I have a theory that it's related to migration. And what you're gonna do with this code specifically is you can relate the two things that need to be related in order to show this theory to be true. Yeah. So even if we don't get very far, but we can just map it, that's a huge deal.
Cool.
Yeah. So I just wanted to make sure to say that because if this is a mechanism, then that basically gives us a time scale for spiral disruption. And each time it disrupts, it should reform again through another mechanism that's actually known.
Okay.
Yeah. Okay. This picture, right, you're just putting a limit to how far stars can actually migrate in a statistical manner. You're adding the statistical component so that do this. Okay. So now let's say we're looking at the disk from the side. I'm going to talk about the way that radial migration, which is what you call it when a star in a trapped orbit moves from one radius to another and is permanently in a different place, right, via one of these trapped orbits. So I'm going to talk about it dynamically, and I'm going to talk about it kinematically. Sorry, damn it, I'm too tired. Kinematically and chemically. So if you were looking at a disk from the side, one of the things we have to take note of is the structure that is ubiquitous within the disk and how can radial migration affect that structure. So we're going to start with kinematics. If you're looking at it from the side, all the spiral arms, most of the stars, all the cold gas, everything lives in this plane, right? It's a very, very thin plane. And let's just call that the center, where the sun is like here. So when you actually, if you'll remember way back, we were talking about the surface density, where this is radius, that's surface density, and we said that there's an exponential surface density for the disk. So now, if you have a group of stars that, here's your co-rotation radius, and you have some stars within this block that are in trapped orbits, and you rearrange them, right? You move some out, you move some in, then the number of stars that are actually moving outward is greater than the number of stars that might be moving inward. In which case, you would effectively be moving mass out. And it's a question, is that something that really happens? Another thing that we know about the disk is that it has, just like the surface density profile is exponential, the velocity dispersion profile is also exponential. So what is velocity dispersion? That means that if you take some, you just pick a coordinate, let's pick the coordinate where the sun is, and you plot the velocities, and you can pick any component you want. It can be radial, it can be azimuthal, it can be vertical, whatever it is. Then the velocities are going to have a spread, and let's just pretend it's Gaussian for now. Which means that at that coordinate, some stars are going to be moving a little faster, some are going to be moving a little slower than the circular velocity, some are going to be moving outward, some are going to be moving inward, but for the most part, they're going to have, if this were, I'm going to color code this, if this were phi, so azimuthal, then this velocity right here would be the circular velocity. But if we were talking about the radial velocity, then this same place, the midpoint, would be 0. So meaning that radially, there's no bulk motion. Stars are just kind of in their something like elliptical orbits. And then we can quantify, how big this spread is using the velocity dispersion. So this is from the Gaussian. This is just the spread.
Are you recording?
I am. Yep. So what that means? No. It's a good question. So, so then what this plot over here means, saying that the velocity dispersion is exponential, that's like saying in the inner part of the disk, there are more random motions. Exponentially, the motions are more randomized than they are out here. So, let me introduce you to something else. That is I'm going to make it green, the thick disk. That is a bunch of stars that are puffy. They live outside the disk, meaning vertically, they're extended. There aren't a lot of stars here. The thick disk is made of old stars. How it got there, we don't know. It's a good question. So one of the theories, though, is that, I'm going to add something to this. I'm going to not use yellow. I'm going to use purple. Is that, let's say, you can have velocities that are vertical, and that is also, that central point is also 0. But the thin disk velocity dispersion is rather small, which is, a star moves above the thin disk, and it feels a vertical forcing downward toward the mass of the disk, and it goes down like this, and it feels it upward, and so it just kind of oscillates vertically. So now, if you look at the thick disk, those stars are oscillating this huge distance. So one of the ideas here is that if you have a star that's at, let's say, I'm going to pick another color, red. You have a star that is here on this map, right? So let's say a thin disk star. And so it's here on that map, and it has a vertical velocity dispersion, this can also be z, that is whatever it is at that place in the disk. Then if that star migrates outside of co-rotation like that, then that means you're taking this star, that vertical velocity dispersion is pretty close to conserved. you're moving it outward in the disk here, where we know that the amount of mass in the disk is lesser. So we can think of this vertical motion as like a kinetic energy term. So that's your velocity term. So then what that means is if you've moved out here and you have this high vertical kinetic energy term, then you can move much farther before the vertical forcing from the disk pulls you back. So in other words, perhaps it would thicken that population. So one of the questions is, if you have not just possible that effectively hops you out enough that you are now a star that makes the thick disk. And since those stars are old, that means that they've lived long enough to migrate long distances.
So thick disk as in like outside radius, or thick disk as in also thicker?
It means it's vertically more extended.
Oh, okay. So
Yeah.
it's not a fried egg, it's more like
It's not a what?
a fried egg.
Friday.
Oh, no, it is no longer a fried egg. It's just this thickened distribution of old stars that we don't know where they come from.
Okay.
And it's just like this envelope that's wrapped around the thin disk. And we see it in all disk galaxies. They exist everywhere. Now, probably this isn't the only mechanism, but it's worth studying just to see how much of a contribution radial migration might make.
To what?
But there's still the galaxy's like nucleus thing.
Oh, the bulge?
The bulge is
Yeah.
still bulgy.
Yeah, yeah. But then one of the other mechanisms might be actually that the bar kind of pushes shit out from the bulge.
Right.
So, okay. I also promised you I was going to talk about chemistry. But Carrie, where your research plugs in is, so I promised I'd talk about chemistry. And I have no idea if this is ordering the video in some weird ass way. Oh, I have to. Turns out that the density of gas follows an exponential pattern just like the surface density of stars. So in the inner part of the disk, we expect star formation rate to be much higher than we would expect it to be way far out here. Right? This, on this map here, right, that's going to take up like this area right here. It's like tiny on the galactic scale. But this picture, let's just use the thick disk thing. These are a bunch of old stars, but if they've migrated from the inner disk, then we should see the signatures of that in their chemistry. Some people say they see it and some people say they don't, observationally speaking, so that doesn't get us very far. But one of the things that we can use in terms of how would this process actually affect the overall evolution of the galaxy, right? So we have this thickening of the disk that could happen. We have the possibility that stars are being mixed up, meaning stars don't stay where they're born, they get moved around across the disk, and might even move mass outward in a way that grows the disk. It might give rise to an extended part of the disk out here that we call the outer disk. So that's Olivia's work, and she's trying to build a model to see if we can actually use radial migration to build this outer disk. And then Cody, one of the things that you're doing is almost the opposite of trying to say that radial migration makes a thick disk, but that in fact, if you have a chaotic orbital response, then it may be that that's scattering stars vertically as well.
Okay.
So it would actually put a limit on how efficient radial migration was, but add a new process that could lead to thickening. Chelsea, what you're doing is, again, you're rather than a spiral, you're looking at whether or not dark matter halos could also contribute to this redistribution. But again, that would also lead to a thickening, because remember what was it called? The orphan stream? So over time, that's just going to smooth out, right? Like all those stars actually have different velocities, and they're just going to get all mixed up with the rest of the vertical structure of the disk, and you wouldn't be able to see them anymore. So as they age, right? So they become old, as they become more extended. So that would be another way to thicken the disk without it having, that might be also related to radial migration, but maybe not completely. And then Jess, what you're doing is very similar to what we were talking about this summer, but effectively, and when we look at how big that leap can be, this red leap, it may not be actually as large as we think it is. It might be a much smaller leap. So it's kind of constraining how efficient this process is. Because if it were really, really efficient and every single time the galaxy orbited at some radius, there was a new spiral that moved stars, then that disk would just be like, bleep, like it would just be, yeah, so we have to limit it somehow, but we have to figure out what is the physics of that. So, that's mostly what I wanted to cover today with everybody, to put it in the big picture. Chelsea, you're already writing something. Yeah. Olivia, you've got a million things on your hands right now, right? But Amelia Earhart's coming. No, sorry, NSF. That's in the beginning of November. So we've got like 3 more weeks.
The end of October.
Shit.
And it's the 27th.
Of October? Oh, but my rec letter is later than your due date.
Yeah.
I have it in as the 2nd. Hmm?
Oh, is it the 2nd? Okay.
That's what I have. Would you double check those dates? Because then, and then right now you're going over your application, right? Yeah. Okay. So maybe before fall break or like over that weekend, see if you can send it to me, because after you've like beat it up and like been really mean about it and done like, yeah, and then because I'm leaving for most of fall break. And Cody, you have a thing that you're writing.
Yeah. What do you mean?
For just you're writing up the relationship between the different parameters and stuff. Yeah. No, not like a big paper yet.
I was like, sure, but.
You're like, yeah, but no.
Yeah,
And then Jess, you're in a place where you're producing these things. So I don't think it's time for you to start writing just yet. Although I really think that it would be good to do that in the next week or two, just so you have that on your radar. But yours is going to be more substantial, because I think you should pull in the stuff that we did over the summer. Because you did a lot of stuff over the summer, and that's totally applicable to your thesis. We just have to write it. Okay, so we're I'm reading it upside down, like 4:45, right?
3:45?
I mean 3:40. Oh, good sweet Jesus, yes, 3:45.
3:40.
3:40. Okay. Do you guys have questions?
So the radial migration, how it like makes the velocity in the z direction become greater. Can you explain that again?
Yeah. So, I mean, and it turns out that it probably is not as substantial an effect as one might think. But the mathematics of that is like, we're not there. So, okay. Okay, so now, chemistry. Chemistry sounds horrible and scary, but it's actually really important and helpful. Because Stars, let's pick, I feel pink today. So stars are made from the gas environment within which they formed. And that's really important because that environment, we have a sense of how it relates to galaxy evolution. So one of the things that we know is that the star formation rate is somehow proportional to the density of gas in some region to some power, right? It's some power law. And then, so if we know that that's true, okay, so expectation, I'm going to say star formation rate, just so you know that that's what I mean. Star formation rate is greater in the inner disk. That's step one. Step two is what happens when you form stars, right? So stars, let's use like I'm gonna use a baby blue-ish thing. You have this cloud, right? That cloud of gas, it's mostly hydrogen, has some other elements. There's hydrogen plus Z just means other stuff. And that gas cloud collapses, and within that gas cloud, you get a whole bunch of stars, right? Those are stars. And those stars have exactly the chemical signature of that cloud within which it formed. Those stars then die. But before they die, in their insides, they fuse elements. And they fuse hydrogen into helium, helium into carbon, nitrogen, oxygen, silicon, iron, right? So they just fuse up the ladder in the periodic table. And the more mass of the stars, the higher the atomic number, and till eventually you hit iron. So you fuse a bunch of stuff, and then they die. And when they die, they make a whole bunch more elements, depending on how they die. But then they die. Oops, I want to make it pink. I'm being a little anal here, but whatever. Then they die. And when they die, first thing they do is they make more heavy elements. And the next thing that they do is they spew all their guts into space. And to give you a sense of like the scale, what that does then is it enriches. It goes like this. And then that comes back around like this. Enriches the gas from which stars form. So now we have a second relationship, right? And I'm gonna say this is step one, big step one. This is big step two, like concept two. So putting these two things together, in the inner part of the galaxy, if you have this high star formation rate, what that means is you're getting a higher rate of this process, which means that the gas in the inner part of the galaxy for the same age star is going to be more heavily enriched with these heavier elements than hydrogen. So if you were looking toward the galactic center and you were looking for a star like our sun, born at the same time as our sun, it would have a lot more heavy elements. And if you were looking at a star-forming nebula near us, it should be more enriched than the sun, because it's forming now and the sun formed 4.5 billion years ago, right? And then if you were to look at something the age of the sun in the outer part of the disk, likewise it would have a much lower chemical composition, much lower number of heavy elements in its chemical composition. So then, well, let's go back. Appears to be more and more true is that the sun has is more enriched, has the same chemical composition as, say, the Orion Nebula, which is really close. Which means that the sun may have been born a few kiloparsecs, so maybe like a quarter of the way, closer to the galactic center than we are right now. Which is kind of neat, right? So, all right. All this said, I want to tie this into your various projects. Because now what we're doing is we're saying, here's the big picture of galaxy evolution. What are the traces? Let me see if I can break it down a little bit more. All right, so let's just say we've got a disk of stars, right? And then in that disk, we have a star, and we're just going to follow it in its circular orbit. We only care about the vertical motions.
Okay.
All right, so it goes up, and it comes down, and it goes up, and it comes down. And this is basically a simple harmonic oscillator, right? So where its kinetic energy up here reaches 0, it maximizes right here, and its potential is minimal. And then again, down here, it has maximum potential energy, 0 kinetic, right? So it's just switching back kinetic and potential energy. It's going up and down in this simple harmonic motion. But the force that's causing it to come back, the restoring force, is gravity.
Right.
So if you have a star, right, we can call, and then if you were to, there's this leap from using the vertical velocity dispersion to relating it to the velocity of a single star, right? Because the dispersion, remember, had to do with like a full population. But you can basically say that that vertical velocity dispersion for the population is roughly equal to the vertical velocity of that star when it's at z equals 0.
Okay.
So then you have a kinetic energy term. And that kinetic energy term is related to the potential energy term by, the simple harmonic oscillation. And the potential is related to the amount of mass that's in the disk. Are you with me so far? Okay. Just tell me if I'm skipping steps and I'm sorry. So now let's imagine I'm gonna do something here. Stop it. So I'm gonna pretend that means that there's a whole lot of mass, right? And that you get down in the outer disk where there's like a lot. I'm gonna totally make a horrible drawing. But they're way out. If you were to move to the right by a long way, then there's exponentially less mass, which means that the restoring force or the potential energy at some given height is going to be much less. So it might help to just that the force is the derivative of the potential. And the potential, well, I'm going to say it's something like that, where that mass is the mass that's like right there. So now you've got your star, it still has the same kinetic energy. In other words, its VZ in the plane is going to be the same thing. So since when it moves out here, it has the same kinetic energy, but it has exponentially less potential energy, then that means it can travel farther before it comes back.
Okay.
Does that help?
Yep.
Yeah? Okay. So, yeah. So now that assumes, the big assumption in all that is assuming that the kinetic energy or the vertical kinetic energy is conserved.
Why wouldn't it be?
Well, it turns out it's not quite.
Oh, okay.
But there's something else called action that mostly is.
Mhm.
It's related. But the final effect is that this puffing up quality is not as dramatic as you would derive if you just use something like this. So it's a little bit of an effect, but not a lot.
Okay.
Mhm. How about you guys? You're like doing your thing. Okay. And Jess, you look like you're in it, whatever you're doing.